Hello, Integrated Math 1. Welcome to lesson 1.2.3b. We're on day 2. So we have a warm-up. We did warm-ups 1 and 2 last time. We're doing warm-up number 3 this time. The deal, the local bank has agreed to donate $250 to the annual turkey fund to help feed families in need. In addition, for every bank customer that donates $50, the bank will donate $25. And the question is, what is the 20th term? We had a formula last time that helped us find that term. So go ahead, hit pause to use the formula and to do the work, and then hit play when you're ready to check your work. All right, are you ready? Remember the formula from last time? Do you remember this formula? Oh, there it is. A sub n equals a sub 1 plus d times n minus 1. Now let's remind ourselves of just a few little things here. You know that n is the term number, and of course in this case it's going to be term number 20. We know that a sub 1 is our first term. Sorry, my pen went a little crazy. I will fix that. Better. A sub 1 is our first term, which is, of course, 250. And, of course, D is our common difference. Well, we're adding in $25. The bank is adding $25 as their customers donate. So my D, then, my common difference, would, of course, be 25. And now that I have all the pieces, I can plug in. So I now have A sub 20 equals 250 for my first term, plus 25 for my common difference, times 20 minus 1, because again, 20 is the term we're looking for. And at this point, I'm going to do a little math. Of course, 20 minus 1, that's easy. That's 19. Grab my calculator. 20 times 19 gives me 475, and we'll add that onto the 250 of the original donation and find that the bank is going to be donating $725. I don't know why the dollar sign appears at the back. I tried to fix that, but something's gone weird on my formatting and I can't fix it. And the dollar sign is now at the back instead of at the front. I don't know why that happened. Sometimes things are weird. So let's jump in here. Page 131, we're still there. So we've been determining recursive and explicit expressions. Now last time we did arithmetic ones, right? And we found the recursive formula for the arithmetic expression. We found the explicit formula for the arithmetic sequences, I should say. But today we're going to push it a little further because we also want to do recursive formulas for the geometric sequences. And we want an explicit expression for our geometric sequence, right? We want to keep this going. And of course, that means there's more formulas. Of course, we're going to be using formulas to determine our unknown terms of a sequence. So we did a lot with arithmetic last time. We're going to push into the geometric this time. So, of course, key terms are recursive formula and explicit formula. We talked about those in the last lesson. And, of course, we know arithmetic and geometric sequences, they make functions, right? Arithmetic sequences give us linear functions. Geometric sequences give us exponential functions. We know this, which means we should be able to write equations to represent these functions. We did that with the arithmetic guys last time. We're digging into the geometric guys this time. So let's just dive in all the way over on page M1-136. So when it comes to bugs, bats, spiders, and any other creepy crawlers, finding one in your house is finding one too many. Then again, when it comes to cells, the more the better. Animals, plants, fungi, slime, mold, and other living creatures are composed of eukaryotic cells. I can say this, eukaryotic cells. During growth, generally there's a cell called a mother cell that divides itself into 2 daughter cells. And then each of those daughter cells divides into 2 more daughter cells, and so on and so on and so on. So the sequence shown here on page 136 just represents the growth of eukaryotic cells, right? You guys have been doing science. You're taking biology. You get it. Cell division, right? It splits and it splits and it splits. So while we start with one cell, After one cell division, we have 2 cells. After another cell division, we have 4 cells, then 8 cells, then 16. Can you just real quick, can you describe why the sequence is geometric? And while you're at it, can you also please identify the common ratio? Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. So, of course, this is totally a geometric sequence because the pattern is that we're multiplying by 2. We're multiplying by a constant, right? And because that constant that I'm multiplying by is 2, that means we have a common ratio of 2. Dun, 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 dun. Now, as we're working, can I just point out one other thing as we're working? There is a little note over here. We had this issue last time with the home runs. Can you notice that the first term in the sequence is after 0 divisions? Did you catch that? 0 divisions, all right? That's the mother cell, so 0 divisions is the first term, which means this is my second term is after 1 division, my third term is after 2 divisions, and on and on and on. You see where it's going, there. So with this in mind, we do have a table. Of course, we have a table that also points out number of cell divisions and all that good stuff. Can you please complete the table of values and make sure that you're noticing that the number of cell divisions and your term number are a little bit offset? Keep a watch on that. Go ahead and hit pause to fill in your lovely table and then hit play when you're ready to check your work. So I'm going to fill it in. Of course, we know, sorry, my lights keep going out. I'm in the dark. So that means my first term is, of course, 1. My second term then is 2. My third term is 4. My fourth term is 8. And my fifth term is 16. If we keep that going, and I have a calculator handy to make sure I do it right, my sixth term then will be 32. My seventh term will be 64. My eighth term, which is after 7 cell divisions, will be 128. My ninth term will be 256, and my 10th term will be 512. So again, can you please notice that my first term is 0 cell divisions. So 1 cell division is actually term 2. 2 cell divisions is actually term 3. 3 cell divisions is term 4. 4 cell divisions is term 5, and so on and so on and so on. I know we mentioned it before, but I'm just making sure we got there. So explain how you can calculate the 10th term based on the 9th term. Just hit pause, jot down your thoughts, hit play to keep going. You know how to do it. Of course, if you have the 9th term, you want the 10th term, just multiply by 2. Duh, we know how to do that, right? No big deal, no big deal. Which, of course, the idea of finding the next term from the term right before it leads us to that recursive formula. Yeah, so we're back to the recursive formula where if I want to know a term, and remember that M is your term number, right? Don't forget that, term number. Then that just means you need to take the previous term and multiply it by your common ratio. Now, because it's geometric, we are going to multiply the common ratio. You know that. The other thing is that it's now an R for a common ratio. It's not a D anymore. That's how it goes. So if I have this lovely sequence here, and it is such a lovely sequence. In fact, I'm going to use this. I think it's easier. Here we go. So if I had this lovely sequence, 4, 12, 36, 108, well, I could use a recursive formula to find the 5th term. So here's my recursive formula. I want the 5th term, so I'm going to put G sub 5 equals the term before would be G sub 5 minus 1. And of course, hopefully you notice the pattern is that we're multiplying by 3. So my common ratio is 3. So that's no problem. And then we can clean up a little bit, right? 5 minus 1 is 4. And in fact, we know what the 4th term is. It's 108. So if I wanted to find the 5th term, I would take my 4th term, which is 108, multiply it by the common ratio, which is 3, and we would find out that our 5th term of the sequence is 324. That's great. But take a look at our table. We're back to our table. Consider the sequence of cell divisions and the total number of resulting cells. can you write a recursive formula for the sequence and use that formula to determine the 12th term in the sequence? And make sure you explain what your results mean in terms of the problem situation, in terms of like cells and divisions and all that kind of stuff. Go ahead, hit pause to write it down, hit play when you're ready to check your work. First of all, I'm gonna bust out the formula. So here's my formula. Boo, yay. I already know what a lot of these things are, right? I want the 12th term, so G sub 12. But I'm going to sum G sub 12 because I want the 12th term. I need the term right before it, so G sub 11. I'm going to multiply by my common ratio. Ooh, we wrote that down earlier, right? We said our common ratio was 2, didn't we? Wrote that down earlier. And do I know what the 11th term is? I don't have the 11th term. I could find it though, right? So I'm going to grab my calculator. I'm going to take this guy here, that 512. I'm going to multiply it by 2. And I find out that my 11th term is 1,024. And of course, if I multiply that by 2, that will give me my 12th term times 2, which is 2,048. Now, I'm going to take my sketchy writing off of here. Hang on. I'm going to get my sketchy writing off of here, and we're going to make it all pretty. So pretty. So our 12th term is 2,048, but the problem said, can you describe what your results mean? Like, what is it that we found here? We found that the 12th term is 2,048, but remember the 12th term is only 11 cell divisions. We've only divided 11 times. So there are a total of 2,048 cells after 11 divisions. The lights, what can I do? They're on a motion sensor, and if I'm sitting at my desk, I'm not moving enough, apparently. It's fine. Now, we've already talked. The recursive formula is great if you just want to find the next term. But if I want to find the 20th term or the 34th term or whatever, I need something better, right? I need something better. So the explicit formula is the one that's going to help us find any term we want. Now, it's different this time because we're now doing geometric, not arithmetic. So our explicit formula has changed. There's some important changes I need you to notice. So, of course, if we want the nth term, and we know that n is the term number, right? We know that. So term number, we know that. You still need to use the first term, G sub 1. And that's like the arithmetic guys. The arithmetic explicit formula also needed the first term. We need our first term for a geometric formula as well. The only thing is we're not adding this time, are we? We are going to multiply because it's geometric. But here's where it gets trippy, and here's why you want a calculator. Seriously? Seriously. Because your ratio, your common ratio R, gets raised to the power of n minus 1. Remember arithmetic, your common difference was times n minus 1? Not anymore. For geometric, you actually have your n minus 1 becomes the exponent to your common ratio. Trippy, right? Straight up trippy. It's crazy. But let me show you how this works. So coming back to our cell division issue, we already know some of these things, right? We already know that the first term is 1. We already know that our ratio is 2. And if I want to find the 20th term, fine, I'm going to say n equals 20. And like I said, for our cells, we already know that r equals 1. We already know that our first term was also 1, so that's terribly convenient. And so we're just going to plug everything in. So here's our explicit formula. G sub 20, because that's the term I want, equals 1, because that's my first term, times, did I write that R was 1? R is not 1, R is 2. See, I don't have you guys here to correct me. Things like that happen. My common ratio is 2, so put that in. And then we're going to give it an exponent of n minus 1, so in this case, 20 minus 1. This is where you got to be real careful. First of all, 20 minus 1, that's easy. That's 19. This is where you need your calculator. I don't know if you guys realize it or not, but your calculator, if you have a scientific calculator, it can literally do any powers at all. It can do it. you have a button on your calculator. Now, your button might look like this, or maybe your button looks like this, like it looks like a little carrot kind of thing, but you have a button like that somewhere on your calculator, whichever calculator it is you're using. And what you do is you type in the base 2, you hit the magic button, whether it looks like this or whether it looks like that, but you hit your magic button, and then you type in your exponent, and then you hit the equals button. And in this case, that if I do 2 to the 19th power, so I'll do 2, magic exponent button, 19 equals, and I get this big old number. I get like 524,288. It's a big number. Yeah. And that's great. Please remember you need to do your order of operations. You need to do exponents before you multiply. Please do the exponents before you multiply. So I did my exponent, multiplied that by 1, and it looks like the 20th term of the sequence is 524,288. This means that after 19 cell divisions, there are a total of 524,288 cells. So we're 500,000 cells after 19 divisions. Crazy! So now that you've seen the explicit formula, you've gotten used to it, you've seen how it works, I would like you to use the explicit formula for number 3. A, B, C, D. I only have A up on my screen, but you have more than that on your book. So can you please do all of these problems? Please remember that the cell divisions are offset. Please remember that your divisions are offset of the term number, so you're going to want to compensate accordingly. Go ahead, hit pause, work your way through this, and then hit play when you're ready to check your work. So I'm going to make some notes. First of all, we know, because they're all doing the cell thing, we know that the first term is 1, right? We started off with one cell, one little cell. We also know that our common ratio was 2, right? It keeps doubling, 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 all of that good stuff. The trick is your term number. Please remember that 11 divisions means you're looking for the 12th term. So when you use your formula, we have our first term, we have our ratio, but n is going to equal 12. Please make sure you plug in the right numbers. So my first term is 1, and then I'm going to do 2 to the 12 minus 1 power, also known as 2 to the 11th power. And that's what I have a calculator for. 2 to the 11th power is 2,048. Multiply that by 1, I get 2,048, which we actually already knew, because didn't we find the 12th term earlier? I'm just saying, we did that. What about after 14 divisions? Please remember that after 14 divisions, it's the 15th term. So if I use my lovely formula, I know this means that n has to be 15. Of course, my first term is 1, my ratio is 2, 15 minus 1 is 14. I will use my magic calculator to get 16,384. Thank you, exponent button. Multiply that by 1, you still have 16,384. That's a lot of cells. After 18 divisions, 19th term. So everywhere I see an n in my magic formula, I'm going to plug in a 19. So G sub 19, that means 19 minus 1 is 18. Of course, we started with one cell, and our ratio is 2. So 2 to the 18th power with the magic exponent button is 262,144. We multiply that by 1, we still have 262,144. And after 22 divisions, please remember it's the 23rd term. So everywhere I see an n, I'm going to plug in 23. 23 minus 1 is 22. 2 to the 22nd power, oh my gosh, is 4,194,304. This is out of control. That's a lot of cells. Multiply that by 1, you still have 4,194,304. Woo! That's a lot. Can we change it up on you? Let's change it up a little bit. Suppose that the scientist actually has 5 eukaryotic cells in a petri dish. She wonders how the growth pattern would change if each mother cell divided into divided into 3 daughter cells. So she's not starting with 1, starting with 5. And instead of splitting into 2, it's now going to split into 3. Can you write the first 5 terms of the sequence for this hypothesis, please? Go ahead and hit pause to write it down. Hit play to check your work. All right, so if we start with 5, but it splits into 3, that means right away after 1 division, I've already got 15 of these things. After 2 divisions, I now have 45 of them times 3, right? Oh my gosh, after 3 divisions, we have 135. And after 4 divisions, our 5th term, we've already got 405 cells. Wow. I mean, I thought the other one got big fast. This is just out of control. So do number 5, part A, part B. Work these out. Determine the total number of cells in the Petri dish for each number of divisions. Go ahead, hit pause to work these out, hit play when you're ready to check your work. All right, first of all, I'm going to point out a few things. Our G sub 1 has changed. We're no longer starting with 1, we're now starting with 5. So my first term has changed. The other thing that's changed is my ratio. My ratio, it's not splitting into 2, it's now splitting into 3 cells. So my ratio has changed as well. And of course, just like before, 13 divisions means it's the 14th term. So n equals 14. So I'm going to plug everybody in to my fabulous formula. So G sub 14 equals 5 times 3, and 14 minus 1 is, of course, 13. And again, I used my calculator. I used the exponent button, 3 to the 13th power, and I got something silly big, 1,594,323, which I then multiplied by 5, and I was glad to have a calculator to do that. And I got 7,971,615. That's a lot of cells. What about number 16? Last one. Number 16, last one. All right, you got this. You know it. 16 divisions is the 17th term, which means my first term is 5. My ratio is 3. 17 minus 1 is 16. I'm going to use my calculator. I love that exponent button. I love that button. 3 to the 16th power is, of course, 43,046,721. Times 5 means it's barely fitting in my calculator anymore. This number is getting big. 215,233,605 cells. Does it even fit in the Petri dish anymore? I don't know. I hope it's a big Petri dish because that's a lot of cells. As always, guys, I hope you found this helpful. I hope you found this useful. If you got questions or concerns, email me, come see me during office hours, come talk to me. I'm here to help you out. That's why I'm here. And I'll see you guys soon. Bye.